welcome back to our second segment. We're still looking into the quantitative aspects of chemical change, but our focus for now is on percentage yield. We want to get a sense or some form of understanding in the sense that, when reactants react with each other, there's what we expect in terms of the yield, or the end product, in as far as the quantity. Then we want to check as to what percentage of the actual, of the theoretical yield is what we get at the end, which is the actual yield. So when we talk about yield, loosely, I think we are referring to the amount of product. Okay, so based on what we put in as far as the reactants are concerned, right? So our focus for now is on yield based on the balanced equation of reaction. Okay, so that's the whole idea on stoichiometry, right? Okay, so the mole ratio in balanced equation, what does it tell us? It tells us that, in stoichiometry, it involves the study of numerical ratios in which reacting substances participate in a reaction. And here it's not just the ratio, it's actually the mole ratio, right? It tells us the mole ratio. Why the mole? I think we've overemphasized the fact that the mole is the SI unit. So, if we talk quantity of a matter or quantity of a substance in a chemical reaction, we shall draw attention to the mole. So the ratio between all substances that are part of a reaction which has reached completion, that's a very important term, is called the stoichiometric ratio. So when you react two reactants, let's go back to the example of the formation of ammonia when nitrogen and hydrogen react. So when we say that the reaction has reached completion, what do we mean? We're saying that the reaction has stopped in the sense that one or both of the reactants has been used up. So once we don't have all the reactants present, then the reaction stops to happen. I think it's logic. Then by that time, we would say, okay, either one or both of the reactants has reacted completely. Okay, so that's how we describe the end of that reaction by using the term completion. Okay, it's a very important term that will have a lot of implications going forward. So that's as far as completion. Now let's look at percentage yield. Okay, so the theoretical yield, right? I'll underline that because that's a very key term in terms of what happens in a chemical reaction. So theoretical yield is the maximum, so that's a keyword, amount of product formed as calculated from the balanced equation of reaction. Okay, so remember, first things first, the balanced equation gives us the stoichiometric mole ratio in which substances react with each other to form the products. So when that happens, we are simply saying that we are able to determine, this is what we expected. That's the maximum in terms of theory, should the reaction reach the end when one of the two reactants has been used up or both, okay? Now, that's the theoretical yield. So in real life or in practice, the actual yield is usually less than the theoretical yield. This is the reason behind that, is that not all reactants are actually converted to products. So there is a comparison between actual yield and theoretical yield. Okay, so in most cases, what we get is not actually what we calculated theoretically. This is what we would expect. Okay, so theoretical yield is what is expected. Okay. So this is the expected amount of product, okay? As per the balanced equation of reaction. It can be product or products, it doesn't matter, okay? So it will depend on the context under consideration, okay? And then, so the percentage yield, in the percentage yield, the actual yield can be used to determine the large-scale production of important chemicals, if it is viable or not. So we have our own expectation in terms of the quantity of the product, but in reality, the actual yield is normally less than the expected or the theoretical yield. So, in terms of application and the practicality of, the importance of percentage yield is that if large-scale chemical production is to take place, in industry. Now, there is as a measure of how economically viable the process is, we have to determine, the percentage yield, which says, okay, this is what we produce, this is what we versus what we expected. Is this profitable? Is it economically viable? Are we using the costs attached to it? Has also those far-reaching implications. So we need to think about that in as far as the application of, percentage yield as a measure of, economic viability of a process that is being carried out in a chemical reaction, right? So how do we calculate percentage yield? Percentage yield is actual yield. This is what we get in reality over the theoretical yield multiplied by 100, because remember, anything that is expressed as a percentage is measured against 100%, okay? So actually the percentage yield would be, in practice less than 100, okay? Right, so here is an example of percentage yield type of a problem. Okay, iron metal is extracted from iron 3 oxide according to the following equation. Okay, take note, this is iron 3 oxide. Iron is a transition metal, so we know from our chemical formula that the ion in this case is 3+, okay, because we're told by that number. It's an indication of the charge or the oxidation number. We'll talk about that later, okay, and then oxygen 2-, which gives us the formula Fe2O3. So that's the oxide of iron. Okay, this oxide reacts with carbon monoxide to give us iron metal and carbon dioxide gas. So the process involved here, our main product of interest is the iron, okay, metal. So we want to extract iron from its ore, okay. So that's the equation, okay. Now the question is, what is the theoretical yield of iron if 150 grams of the ore reacts completely? So if it reacts completely, we're saying if this reaction reaches completion, what is our theoretical yield? So we're going to use the stoichiometric ratio in which these substances react to try and determine that. But before we do that, first of all, we need to actually calculate actually balance the equation, right? So in balancing the equation, that's the first step, okay? How many atoms of iron do we have on the left? It's 2, okay? So for us to balance, if we put a 2 there, it looks okay for iron for now. And then if we go to carbon dioxide, okay, carbon monoxide versus carbon dioxide, because both of them, they actually contain carbon, okay? Because our focus is not so much on the balancing, but balancing becomes an important part of our problem solving. So if we have, let's say 3 here, and then also another 3 there, let's check if it's balanced. How many ions do we have on the left? Is 2, on the right is 2. Let's go to carbon, 3 on the right, and then oxygen, we've got 6, 3 plus 3, and then 6. So the stoichiometric ratio in which these substances react with each other is 1:3, 2:3. So that's the stoichiometric ratio in which they react with each other. So the question, if we can go back, it wanted us to calculate the theoretical yield of iron if there is 150 grams of the ore. This is the ore that we are talking about, the iron 3 oxide. Now let's look at the conversion of the mass into the SI unit, which is the mole. So the stoichiometric ratio in which they react with each other is actually 1:2. Okay, this is the ratio for the ore to the iron. So we are told that there is 150 grams of the oxide, okay? So if there is 150 grams of the oxide, we ask ourselves, in 150 grams, how many moles of iron 3 oxide are present? So we know that number of moles of iron 3 oxide is it actually equals to the mass of the sample divided by the molar mass. So the mass of the sample in this case, we are told is 150 grams, okay? Now, the molar mass of iron 3 oxide, if you go back to the periodic table, you'll get 160 grams per mole, okay? So if we go to our calculator, just to check the calculation there, we'll have 150, that's the mass of the sample, divided by the molar mass, which is 160 grams per mole. This gives us, as a decimal fraction, 0.94. So in other words, what are we saying? We are saying that in a 150 gram sample of iron 3 oxide, there is 0.94 moles of the oxide, all right? So that said, it means that the number of moles is equals to 0.94 moles, right? Now, what do we know? We know that a mole of iron 3 oxide produces double the number of moles of iron. So the number of moles of iron in this case, which will be formed, is equals to, you know, the double that, which is 2 multiplied by 0.94, okay? Which is 2 multiplied by 0.94, right? So the number of moles of iron that will be obtained, okay, from the stoichiometric ratio is, if we go back to our, so it's 0.94 multiplied by 2. This is the number of moles, which is 1.88. So there's 1.88 moles of iron, okay? 1.88 moles of iron will be formed, right? Okay, so what's our next step after that? Step number 3. We can calculate the number of moles of the substance. We've managed to do that. We said number of moles of the product is equals to 1.88 moles. Okay, so where did this come from? It came from the stoichiometric ratio of a mole of the oxide produces 2 moles of the iron. So that is straightforward. Okay, what is the next step after that? We want to calculate the mass of the substance, okay, based on the stoichiometric ratio. What do we know? We know that a number of moles of iron is equals to mass of the iron that will be formed divided by the molar mass, right? So what do we have now? We've got the number of moles, which is 1.88, right? This is equals to the mass, the mass in this case, we just want to check what is the mass of the iron, okay? This is what we have to get at the end. So we are saying that we are looking for the mass of the sample that will be formed divided by the molar mass of the iron. So the molar mass of iron, atomic mass, is 56 grams per mole, okay? But remember, the stoichiometric ratio is still 1:2. So here it's, we'll have our mass is equals to the number of moles, which is 1.88, multiplied by the molar mass, which is 56 grams per mole. So what we get here is the actual mass of iron that will be, the theoretical mass of iron that will be formed from, you know, the stoichiometric ratio. So if we go back to our calculator, what do we have? We've got 1.88, which is the number of moles, multiplied by 56 grams per mole. So what we'll get here will be the mass in grams of what is expected, okay? So what do we get there as a decimal fraction? It's 105.28, okay? So the mass is actually 105.28 grams, okay? So that's how we determine the mass of iron. So this is the mass of iron theoretically that must be formed, right? Okay, so in terms of, you know, calculations, we are able to say, okay, if this is the number of moles in which these substances react, we'll use that stoichiometric mole ratio to actually determine, you know, the theoretical yield. So theoretical yield is actually what is expected. But in reality, if we go back to that question very quickly, where we are told that at the end, before we looked at those steps, it says if the actual yield is 87.9 grams, what is the percentage yield? So we must express this as a percentage of the theoretical yield, okay? So this is 87.9, okay? So if we go back to that, we have 87.9 is the actual, okay? Actual yield is equals to 87.9 grams, okay? And then theoretical is what we calculated, Okay, so our theoretical yield is what we calculated. If we go back, that value is 105.28. So that's what we expected, 105, okay, 0.28 grams. So percentage yield in this case becomes actual yield, which is 87.9 divided by 105.28, okay, that expressed as a percentage. So our percentage yield in this case would become, if we go back to our calculator, it will be, in this case, 87.9 divided by 105, okay, 0.28, right? That, then we multiply this by 100. It gives us the percentage, which is 83.49%, okay? So that's 83.49%. So this is how we managed to determine the percentage yield of this extraction of iron from the ore. So that's how exactly we carry out, you know, calculations as an example based on percentage yield. When we come back, we'll look at more problems in terms of the yield and, you know, percentage yield. Let's take a short break for now.